You know, there is a massive and honestly kind of intimidating gap between learning electrical engineering formulas in a university lecture hall and the harsh, high-stakes reality of actually designing a 150 megawatt utility-scale PV solar plant. In the classroom, well, everything is theoretical, but out in the field, a single miscalculation in your medium voltage network can literally cost millions. So today, we are unpacking the ultimate bridge between those two worlds.
To bridge that gap, we're diving into a really fascinating roadmap, Mastering PV's Summer Training Program. It's fully detailed in this certified book published with Lab Publishing. Now, this isn't just your standard run-of-the-mill textbook. It's a comprehensive, highly technical guide built specifically to transition engineering students and professionals into fully capable EPC, that's engineering, procurement, and construction engineers. It perfectly balances high-level academic theory with raw, on-the-ground professional practice.
To really grasp the scope of this program, we'll quickly walk through its core structure. First, the target audience. Second, Level 1 CNI fundamentals. Third, Level 2 utility-scale projects. Fourth, software mastery and field execution. And finally, the professional outcomes. All right, kicking things off with Section 1, the target audience. Right out of the gate, the curriculum makes a very clear distinction about who this is actually for. It's heavily targeted at senior electrical, mechanical, and renewable energy engineering students in their third or fourth year, plus fresh graduates and junior engineers transitioning into EPC roles. But who is this not for? Well, the documentation explicitly states this is not some basic introductory awareness course. No way. It's a rigorous professional deep dive designed strictly for engineers who intend to design, review, and approve real PV and MV systems at a true industry level. Moving right along to Section 2, Level 1, CNI Fundamentals. In this first phase, that foundational academic knowledge is actively transformed into real design capability. Level 1 covers the first 3 chapters of the book, focusing on solar PV fundamentals. But trust me, it goes far beyond the basics. You actually develop complete DC and AC electrical design capabilities for commercial and industrial, or CNI systems. Crucially, it integrates advanced industry tech right away. You're learning how to design grid-connected systems, solar pumping solutions, and battery energy storage systems, or BESS, using proven, real-world methodologies. Which brings us to Section 3, Level 2, Utility-Scale Projects. Chapters 4 and 5 are where we see a massive leap in scale and complexity. We are moving way past commercial rooftops here. Trainees are engineering entire mega-scale utility solar plants. The curriculum takes a deep dive into medium voltage, or MV, network design. You're learning how to engineer protection systems, design substations, and handle super complex grid interconnection requirements. And it ensures every single integrated PV-MV design strictly aligns with recognized international standards. Now look at the sheer dedication required to actually absorb all of this. 90. That is the total number of hours this program demands. It's a highly intensive, 1-month commitment designed to completely immerse you, acting as that ultimate bridge between the classroom and real-world industry practice. Next up is Section 4, Software Mastery and Field Execution. So how are those 90 hours actually spent? Well, the program operates on a really simple principle. You don't just sit and observe, you execute. In the office-based software track, you're utilizing the exact same suite of tools required by top-tier EPC firms. You'll run full system simulations and yield analyses in PVsyst. You'll do 3D layouts and shading studies in SketchUp. You're drafting electrical layouts and single-line diagrams in AutoCAD. And you'll perform complex power systems analysis and relay coordination using ETAP. And then you take those digital designs straight into the real world, contrasting that digital software environment with raw, hands-on fieldwork. The program actually mandates on-site practical installation. Look at these trainees in action. They're out there physically installing PV modules on steel mounting structures, assembling combiner boxes with protection fuses, handling the earthing systems, and wiring up the solar inverters. It is a complete, tactile reinforcement of all that digital theory. To give you a real taste of just how highly technical this fieldwork is, check out this methodical 6-step sequence for powering up a grid-connected inverter. Trainees don't just flip a switch and cross their fingers. They start with pre-commissioning verification of grounding and surge protection. Then it's a sequential power-up of AC and DC breakers. After that, they establish communication networks, set the power factor and zero export limits, run grid compliance tests for anti-islanding, and finally activate the SCADA system to monitor the initial yield. It is incredibly thorough. Finally, we reach Section 5, Professional Outcomes. So, after 90 hours of absolute grinding through theory and fieldwork, what is the tangible result? Well, this brilliantly illustrates the caliber of the work being produced. What you're looking at right now is a complex, professional outdoor main distribution panel, single line diagram, or SLD. This is not some pre-made template handed to the students. This represents the exact level of detailed engineering drawings that trainees will independently produce by the end of the program, completely ready for client approval. And honestly, that diagram is just one piece of a massive engineering deliverable list that students generate. By the end, they've created a complete base design package. We're talking comprehensive drawings, deep calculations for voltage drop and cable sizing, full PV syst and Homer microgrid simulations, and highly detailed design basis and bill of quantities reports. You walk away with a physical, professional portfolio that definitively proves your competence to any future employer. Now, logistics. How do you actually attend this? The program is highly accessible, offering two modes. The offline mode is held in person at the ASST building in Cairo on Saturdays and Tuesdays. But if you're outside Cairo, there's a live-streamed online format via the ECO platform. However, here is the absolute crucial point. Regardless of whether you attend in person or online, that physical, hands-on field visit at the end is absolutely mandatory. You simply cannot complete the program without proving your skills in the field. Ultimately, surviving this intensive gauntlet earns you a highly respected certification, officially verifiable by the Egyptian Ministry of Foreign Affairs. It's a true stamp of professional readiness. So, considering the massive gap between classroom theory and high-stakes field execution, here's the big question you need to ask yourself. With a verifiable certification and a complete professional engineering portfolio in your hands, are you finally ready to leave the theory behind and power up your EPC career? Okay. Let's dive right into this by looking at the expert behind this rigorous documentation.
You ever flip a light switch and just wonder, about the massive, crazy, complex system that makes it all work? And more importantly, who are the people actually building all of it? Well, that's what we're digging into today. We're going to follow the story of how our world gets powered up, all through the career of one incredible engineer.
So, let's start with the big question. What does it really take to power a whole country? I mean, think about it. Millions of homes, huge factories, entire cities. The scale is just mind-boggling, right?
Okay, get ready for a number. 7 gigawatts. Now, to give you some perspective, just 1 gigawatt can power hundreds of thousands of homes. So we're talking about a colossal amount of energy here, the kind of power that literally changes a country's landscape.
And here's the crazy part. A number that huge, it can be traced back to the work of individuals. That 7 gigawatts, that's the scale of national projects that a single engineer, a guy named Amir Elwani, helped build. So yeah, this is his story.
All right, so every expert has to start somewhere, right? They've got to learn the fundamentals. And for an engineer, that means getting your hands dirty. It means learning how things break and, crucially, how to put them back together. This was the first and maybe the most important phase of his career.
So let's look at the timeline. It all kicks off in 2010. He's a maintenance officer in the Egyptian army. From there, he jumps to a high-tech Samsung factory. Then he's leading a whole section at Universal Factory Group. You can see the progression, right? Each step is a clear level up in responsibility, all leading to him becoming a technical project manager at Giza Power. And all that time, he was building this incredible toolkit of skills. We're talking everything from military-grade diesel generators to the super sophisticated control systems you find in modern factories, like PLCs and SCADA. This isn't textbook stuff, This is real, hands-on experience, keeping the lights on when the pressure is high. It's the foundation for everything that follows. Okay, so with that solid foundation in place, the game completely changes. The scale just explodes. He pivots from, maintaining systems inside a factory to designing and building the actual backbone of an entire nation's power grid.
And when I say the scale is massive, I mean it. Just one project, the Hayakarima Initiative, was a 5-gigawatt project. This wasn't just building another power plant. No way. This was a nationwide program to completely rethink how and where electricity gets delivered.
So you have projects like Hayakarima, which was all about rural electrification, literally bringing reliable power to communities that were underserved, many for the first time. And then you have something like the East Port Said project,
another huge one at 1.2 gigawatts, which was about beefing up the main transmission grid. You put those together, and it's just a gigantic leap forward for the country's whole infrastructure.
So after you've kind of mastered the traditional power systems, what's next? Well, you look to the future, right? And that's exactly what happened here. A really smart strategic pivot into renewable energy, focusing specifically on the field that was just exploding, solar power. And when we're talking about solar, we usually mean photovoltaic systems, or PV for short. Super simple concept. It's the tech, the panels, that turn sunlight straight into electricity we can use.
And you want to know how you can tell someone's getting serious about a new specialty? Look at this. His master's thesis wasn't just some general paper about solar. No, it tackled a really tough, super important challenge. How do you get all that solar energy to play nice with the existing power grid smoothly and reliably? This is the moment he goes from being a generalist to a true specialist. So now he's armed with both the deep academic knowledge and all that practical experience. And the impact? It goes international. This is where the story really takes off, with him leading design teams on huge projects that span the entire African continent.
So now we're talking about 150 megawatts of solar. And yeah, you might think, hey, that's smaller than the gigawatts we were talking about before. But this is different. This represents super specialized, utility-scale renewable energy projects, the kind that are defining the future of power for whole regions.
That 150 megawatts, that's the grand total from all the solar plants he's helped design across a whole portfolio of projects. We're talking about bringing clean energy to multiple countries and literally changing the energy map of the continent.
And you can see the footprint on a map, a massive 60-megawatt plant in Zambia, another 50-megawatt plant in Kenya, plus big projects in Ghana and back home in Egypt. Every single one of these is a huge step forward for that country's clean energy goals.
But at the end of the day, a career like this isn't just about the megawatts. The real lasting impact, it comes from building more than just power plants. It's about building knowledge and empowering the next generation of engineers.
This is what you'd call a force multiplier. Think about it. He publishes research, so he's sharing what he knows with the whole world. He's a certified trainer, so he's teaching students directly, and he mentors younger engineers, passing down everything he's learned. Each of those things multiplies his impact way, way beyond any one project he built.
Wow, his industry footprint is just massive. We're talking about someone who has personally designed 150 megawatts in PV projects and handled an astonishing 7 gigawatts in medium voltage systems. Backed by 3 published papers, his credentials really prove why this material is the definitive, heavy-hitting guide you need for a career in the solar industry. Thanks for joining me on this explainer, and as always, keep learning.